Hey, so this time we're going to be looking at the physics of states of matter changes. So a couple of things that people don't realize with states of matter changes is that, okay, let's say that we have, we have a pot boiling on the stove, right? So the water is in there, you're boiling it. Hey, we'll turn the heat up, right? We got the heat under here. That's what heat looks like. We're going to turn this up higher. Yeah, so then this is boiling, more vigorously. So it must be cooking my food faster. Not so. Actually, what's happening at this point when the water is already boiling? It's going to be 100 degrees Celsius, and it actually will not go above 100 degrees Celsius. The water will actually stay there, and all the extra energy that you're putting in is only going into making those liquid particles. So let's say these liquid particles are kind of together into the gas state, right? So what's actually happening is all of the energy that you're putting into the liquid at this point is not going into raising the temperature, but it's going into changing the arrangement of the atoms from the liquid state to the gas state. So at those states of matter changes, it takes energy to put them into these arrangements and take them out of. Or actually, usually it releases energy to go into them, and then takes energy to take them out. So we have things like this. This is going to be like a state of matter sort of graph, let's say. So I'm going to go ahead and draw this for you. And so there's these plateaus. And what's happening at these plateaus? Well, this first plateau right here, we would say we're going to have melting occur. And that's a change in state of matter from, so down here we have the solid state. So let's say that we've got water. And let's say that we start with our water down here at negative 30 degrees Celsius. Okay? So what's going to happen, let's say that we want to take our water all the way up to 130, right? 130 degrees Celsius. So at 130 degrees, what's the water? Well, at this point, up here, the water is going to be gas, right? So those particles are going to become gas. So what we have to do is we have to add enough energy to get it all the way up to 130 degrees. And here's how the energy works. And so say that as we go up, this is temperature, right, increasing as we go up. So we've got our temperature, and so this is going to be actually this is energy. So we have energy going in, and then as we go this way, we have temperature increasing. Okay, so what's going to happen is you're gonna start heating this water, and it's going negative 29, negative 28, so on and so on. Then when we get to here, it's going to be 0 degrees. Now what's going to happen is you're going to keep heating it, but that water will not change from 0 degrees to 1 degree until all of the ice has turned into water, until we get through this melting stage right here. And so what do we call this? We actually call this the heat of fusion. And so this is called the heat of fusion, and the heat of fusion is kind of symbolized with this, heat of fusion kind of symbol right here, this H sub F, and it's joules per kilogram. It's kind of similar to specific heat. It's its own little specific heat per, here, let me go ahead and write this a little bit more clear. It's its own little specific heat per thing. So everything is going to have a different state change, heat of fusion. And then up here, we're going to call this, this is called the heat of vaporization. So we have H sub V. There's actually an amount of energy specific. So for example, for water, the heat of fusion is actually 3.34 times 10 to the 5th. So 3.34 times 10 to the 5th joules per kilogram. So for 1 kilogram of water, you need to add 3.34 times 10 to the 5th joules of energy to actually take it from the solid state to the liquid state. And once we're in the liquid state here, then the temperature will increase. Then all of the energy goes into increasing the temperature. So actually at these points, we would have our, at all of these sloped places right here, we're going to have our Q equals MCAT, right? So this is just going to simply be our amount of energy that's going in to cause the temperature to raise, along with the specific heat of water. All right, so let's go ahead and then figure out, let's just go through and figure out how much energy total would it take. Let's get our heat of vaporization up here. So how much energy does it take to vaporize? And then we'll look at how much energy would it take total to go all the way from -30 up to 130 degrees. So we have 2.26 times 10 to the 6th joules per kilogram. So you'll notice it actually takes more energy to get those molecules from the liquid state into the gas state. And this should make sense because this is a really higher energy state anyways in gas versus liquid. And the transition from the solid to liquid here isn't quite as much. But you'd see that it's actually it's fairly close, and it takes a significant amount of energy to melt the ice. So this would mean that, you know, just like your pot of boiling water won't ever get above 100 degrees Celsius until it's all gas, which isn't going to help you much. Your ice, if you have water, right, and you throw some ice cubes in there, right, or if you get just water and it's, you know, really cold, maybe it was in ice, so it's just say it's already ice water. This water actually over here is going to end up colder than this one. And why is that? Well, because there's going to be a ton of energy input going into this ice just to turn it into water. And that's going to suck energy from the surroundings, and that's going to make the surroundings cooler, whereas this doesn't have that. And so the heat of fusion right here makes your water a lot colder than just having cold surroundings. So this is why we put ice in drinks, to make them colder real quickly. It's actually because of this physics concepts right here. So let's go ahead and take a look at this problem right here. Okay, so we have we also have to think about the specific heat. Now, the specific heat basically when we're adding energy into here doing our Q equals MCAT is actually different for a solid, liquid, and gas of the same thing. So for water, the specific heat of solid water is actually going to be about 2,000 joules per kilogram, whereas the specific heat for liquid water is going to be 4,000 joules per kilogram, and the specific heat for the gas state is somewhere around 2,000. So we have to make sure to add that in. So we got a lot of different things going on. We got to break this all up. So how much energy does it take? Well, so first of all, we're starting at -30 and going up to 30. So that's going to be a change of 30 degrees. So we're going to have a Q equals MCAT. So let's say that our mass of water is 50 milliliters, which equals, well, let's just go with 500 milliliters, so that's half of a kilogram. So we're going to use kilograms in this. So let's say we have 500 milliliters of water, and we're going to heat this up. So let's go ahead and figure this all out. So what's my total Q? What's my total amount of energy it's going to take to get my water from -30 to 130? All right, well, first of all, we're going to have to do this leg right here. So we're going to have our Q equals MCAT. So we're going to have our mass, which we just said was 0.5 kilograms, right? Times our specific heat of ice, which is going to be 2,060 joules per kilogram. Okay, so we have 0.5 kilograms, and we're going to have a temperature change of 30 degrees. So we have a 30-degree temperature change. And so because we're going -30 to 0. Now we're going to have to go plus. We have to factor in this plateau right here. So what is this plateau? Well, we're going to need our mass again, which is 0.5 kilograms. We're going to have to multiply that times our heat of fusion, which in this case is 3.34 times 10 to the 5th, right? And then what are we going to do? So now we're going to add here, we're going to add our Q equals MCAT for this leg right here. And so from this one we have to go and change from 0 here to 100 because it's going to boil at 100 degrees. So this is going to be our mass. We have 0.5, right? Times our specific heat of water is actually 4,180 joules per kilogram. Okay, and this is times 100-degree change, right? So now what we're going to have to do is add. Now we've gotten ourselves to right here, so we're going to have to add in here. I'm going to have to wrap down around here. I'm going to have to add my heat of vaporization because it's going to take energy to turn it from a liquid into a gas. So what's that going to be? Well, I got my mass again times my heat of vaporization. We said our heat of vaporization was going to be 2.26 times 10 to the 6 joules per kilogram. So we have the amount of kilograms, and we have that. Now there's no temperature change here; it's just state change. So of course we don't have to put temperature change in that one. And then we have this final leg right here, which is going to take us from 100 degrees to 130 degrees. So we have once again our mass, Q equals mass times specific heat times change in temperature times our specific heat of a gas. So water in the gaseous state is going to actually be about 2,020 joules per kilogram. Sorry about that. And we have, in this case, a 30-degree change again because we're going from 100 to 30. So if we go ahead and multiply these all out and add them, we're going to end up with an overall Q. So I'm not going to do that real quick. You could all easily do that. But you could see if you're asked to calculate the amount of energy change and you're going through states of matter changes, you have to add in separately the amount of energy it takes to remove them from their state of matter. Because it takes energy to rearrange those molecules from liquid gas to solid state. All right, so in the next video, we're going to look at the laws of thermodynamics and how we use this to run cars and such, and do a few problems that way. So stay tuned.